Any questions on what I said so far? So the main message was that if you take any parametric integral, actually all I said had nothing to do with Feynman integrals, right? You just take any polynomial with positive coefficients, and you look at this type of integral where you integrate this polynomial to some power, then you can always characterize the domain of convergence of this integral in this geometric way. And in particular, the upshot was that if the dimension of the polytope, so if you have enough monomials, if your integrand is general enough, if it's not constrained to some, so this degeneracy, if the dimension of the polytope is smaller than n, this means that actually the polynomial only depends on smaller than n variables. So you could find a change of variables where your integrand only depends on fewer variables. And of course, then you have a problem, because then you have an integration over a variable that nothing depends on. And no matter what you do, you cannot give this a well-defined value. So in every sensible situation, you have a full-dimensional polytope, and you have this non-empty domain of convergence. And then because the integrand is holomorphic, whenever the integral converges, it will also be holomorphic. So you know that the Feynman integral is a holomorphic function of the dimension and the ends, at least in this little inside of the polytope. Yeah? So there is a non-empty region where the integral that we wrote down defines a well-defined holomorphic function. So now there's a theorem about the analytic continuation. And this probably should be attributed to several people. So there's Bernstein, who proved it with different methods in a much more general context, and in another sense less specific than what we do, but he definitely is to be credited here. I think that was the 60s or the 70s. Then there's Speer, who did it in particular for Feynman integrals. And then in this very general form where you forget about Feynman, I mean, Speer is Feynman integrals. This Bernstein is arbitrary holonomic D-modules. So this is very general, has nothing to do with Feynman integrals. Even goes beyond polynomials. And then there is, I think the most readable, if you want to look into this, is Berkish et al. There's some symbol for and. Where they do this in this full generality for arbitrary polynomials. So the claim is, well, first of all, we already discussed there is a well-defined holomorphic function by the integral somewhere. So these integrals and some polynomials to some powers extends, so from this region wherever it is well-defined, to a meromorphic function with poles. So meromorphic means that it's a rational, that it has singularities on codimension 1 devices. So in this case, it's only hyperplanes. All the singularities will be on hyperplanes, with poles on hyperplanes. In general, you could imagine the function having a singularity when d squared plus d minus n1 is 0. But we don't know this from Feynman integrals. So Feynman integrals, the poles and the regulators in the dimension are always linear equations. So nothing like that. So only have linear equations. And we can be more specific. These poles are translates by integers of the facets of the polytope. So let me just explain this in the example. So again, looking at our one-loop bubble, where we had this triangle, we have these three lines. And remember, this line here was the line where n1 plus n2 minus d over 2 equals 0. This here is the line where n1 minus d over 2 is 0. And this here is the line where n2 minus d over 2 is 0. And obviously we have poles, right? We show that the integral diverges when we go to the boundary. So in here the integral is convergent, but if we go to one of these hyperplanes, we must have a divergence. So we get poles on these hyperplanes. But this is only the first pole we see. Remember the gamma function. There's also a pole at 0, but then when we do the analytic continuation, there's another pole at -1, another pole at -2, another pole at -3. And the exact same thing happens here. So you have translates. So you have another pole here where, maybe let me write it like this. Actually, it should go through to this point here. Sorry. It should go through this one. So it's very difficult to draw proper diagrams on this blackboard. So here, this is the line where n1 plus n2 minus d over 2 is not 1. It's not 0, but -1. And the claim is there's also a pole on that hyperplane. And then you can keep going. You can translate this by integers, and you get poles on all of these copies of the facet. And similar with the other ones. So you also get a pole here, and you get poles up there. There's quite a lot of poles, but this is exactly what you expect. Yeah, and just to remind you why you expect this, well, this integral that we looked at, well, you've all computed this at some point. So this is minus p squared minus d over 2. And then you have some gamma functions, d over 2 minus n1, d over 2 minus n2. There is a d over 2 here. And there is a gamma of n1 plus n2 minus d over 2. If you don't remember this, you can do this as an exercise. This is the thing that I told you not to do in the beginning. Because for me it's obvious, right? The denominator doesn't play a role. It's the dimension is positive. Forget about it. The only poles are exactly the poles of these gamma functions, and they are exactly when d over 2 minus n1 is 0, or -1, or -2, or -3, here, and so on, right? So from this explicit formula, you see immediately that you have poles on these lines. But the point is, in general, you will not be able to write a Feynman integral in this form. Then you don't know what happens. But the statement is that you can always read out the poles from the Newton polytope. You just take the facets and you translate them by integers, and you will always have poles on these. And you can make further claims. So this is the structure of these functions. So in particular, when you think of dimensional regularization, right, then this dimension will then usually will put these n's to be integers, or just 1 or 2, if you have propagators to a simple power. So this will be a linear equation in epsilon. You will have a pole at this value of epsilon, but also when epsilon is 1 less, so epsilon is 2 less. So you usually get poles at a whole array of dimensions, always dimensions shifted by 2, or epsilon shifted by 1. This is exactly what you're familiar with, if you think about it. Now the other statement that's important that goes into the proof of this, in principle you can all, the proof is actually elementary. And what you do is you do integration by parts. Just as we did for the gamma function. Remember, for the gamma function, what we did is we took the variable, and when x was 0, this is where our divergence was in the gamma function integral. We had the x to the n minus 1. When n was negative, then we had a divergence. So we did an IBP, integration by parts with respect to this variable. And this happened to increase the domain of convergence and also introduce a denominator, 1 over n. And you can do this with arbitrary numbers of variables. What you do is, for each facet, for each potential singularity, you change variables such that one variable is precisely parameterizing this, is becoming this rho that we introduced. And then do an IBP with respect to rho. And what happens is that you move the singularity 1 further out, and you get 1 over the exponent of rho in the denominator. So I hope I illustrated that this works. You can read up the proof. But this is a general proof how you can show that a Feynman integral, so in particular this applies to Feynman integrals, that even in the cases when you cannot write it explicitly in gamma functions, it always has a well-defined unique meromorphic continuation, you know where its poles are, and more importantly, via this integration by parts procedure, you can derive an explicit integral representation for the integral that converges in this, wherever you want to evaluate it. I think I will come back to that at some point. So are there any questions about definition of dim-reg and analytic regularization at that point? Perfect. That was the idea. So now you can explain everyone what dim-reg is. Now, on purpose, I stressed several times that this is completely general. It has nothing to do with Feynman integrals. So what is special about Feynman integrals? Now let's specialize. Well, of course, I mean, I don't have seen a lot of textbooks for Feynman integrals where you have Newton polytopes and you look at facets and stuff. So there must be a special property of Feynman integrals that allows you to somehow circumvent this or shove it under the rug in a way. And what is the observation is, so the observation is that in most cases, the facet normals of this polytope have the same coordinates, or have only two coordinates. I.e., what I mean is, it suffices to consider scalings where we scale the variables such that lambda a is either 0 or 1. Yes, because in general, I made the point that even though we didn't do it in the example, but in general, you could imagine if you draw a Newton polytope, that it has very weird angled facets. The special thing here is that the normals, right? We only have the normal here is the vector 1, 1, and we have the vector minus 1, 0, and 0, minus 1. But we don't have something like 2, 3. We don't have a weird scaling. So it is enough to scale all the variables with the same power of rho. So either you leave variable alone, or you scale it all with the same power of rho. This is the point here. Okay. So the only thing you have to say is, I mean, you can also maybe say plus or minus here, yeah, but fix the sign. Maybe let's put the plus minus here. So you only have to tell me which variables you want to scale and which variables you don't. And the claim is that in most cases, I can make this more precise if you want, it is enough, and all of the facets will be will be included in these constraints. So you only have to tell me which set of variables you want to rescale, so we can think of them as a subgraph. So think of your big graph as a couple of edges. Now you take a subset of the edges and you scale the variables associated with the edges in the subgraph. Now we have to figure out what is the scaling degree of such a subgraph that is rescaled. So the little lemma is the following. So consider a subgraph inside your big graph, and let xa go to rho times xa for all a in the subgraph. This is what I wanted to stress here. Then the u polynomial of the graph for small rho becomes rho to the loop number of the subgraph times the U polynomial of the subgraph times the U polynomial of the quotient graph. I will explain this in a second. Plus higher order stuff. So O of rho to the loops in the subgraph plus 1. Sorry, this is a bit squished. So there's two statements in this relation. So the first is that it's telling you the scaling degree. It's telling you that the U polynomial scales for small rho with the power rho to the number of loops of the subgraph. So it tells you exactly what omega is, therefore. And not only that, it tells you not only that this is a scaling degree, it also tells you the leading coefficient. It tells you that in this limit, you can actually factorize the polynomial into two terms, which are related to two different graphs. So how does this go? Or maybe let's do an example. So let's look at the graph. Let's look at such a graph. And let's look at the subgraph. Let's say this is our subgraph gamma, consisting of the edges 1 and 2. And suppose these are the other edges, 3, 4, and 5. And now let's look at the U polynomial of G. Remember, this was built out of spanning trees. So we have to look at all spanning trees of G and look at the edges which are not in the spanning tree. And there's very different things that can happen with regard to the power counting. Because, for example, let's look at the tree. Let me draw the tree here. Let's look at the tree which is only the edges 3, 4, and 5. Right, so this gives you the monomial because you're missing out x1 and x2. This gives you x1 and x2. And under the scaling, this comes with the factor rho squared because they're both in the subgraph. They're both getting scale. There's also other trees. You could also take the tree, say this one, right, where you forget about this edge and you forget about this edge, but you keep 4, 5, and 1. So this contributes the monomial x2 times x3, but it only gets one power of rho because only x2 is from the subgraph. The other one doesn't get scale. And you get more terms. But what you notice is that this is the only one which is quadratic in rho, because you cannot leave out more than 2 edges in gamma because there is only 2 edges in gamma, right? You cannot have more edges, more x's from there. You already have all of them. Now there's other trees which you can draw. You can swap 1 by 2 or do some other things. So there's other terms here which are linear in rho, but there's no terms constant in rho, because constant in rho would mean that you have both 1 and 2 included in your tree. But you can never have 1 and 2 in a tree because 1 and 2 is a loop. Right, so you see that your U polynomial is, with respect to rho, it has 2 terms. It has a linear term in rho and a quadratic term in rho. And lo and behold, so this lowest power of rho, which is 1, and 1 is the loop number of the subgraph. And this is, you can convince yourself of this very easily. It's just because if you have a subgraph and you want to select a tree, so in order to have the smallest power of rho, you want to have as many edges as possible from the subgraph. But you can never have a loop. So the best you can do is to take a subtree in gamma itself. Right? In this case, 1 itself is a tree in gamma. Here we don't have anything in gamma. Here we have a tree in gamma. But you can never have more than a tree in gamma because then you would have a loop. But if you take a tree in gamma, then the rest, every other edge gives you a loop in the subgraph. I mean, it's really, if you sit down, you can really work this out. It's a very simple argument. And the other thing is that, okay, so let's suppose now we look at this leading term. So I just explained to you, it means that we have to select a tree in the subgraph. So we will get all the trees in the subgraph. And it doesn't matter which tree we choose in the subgraph because it just means that all of the things are connected without a loop. So it doesn't matter what we do in the rest of the graph. It doesn't matter, like if you have a big graph and you have your subgraph gamma, if you choose a tree, which happens to be a tree inside, so such that when you look at the edges just in gamma, it's a tree of the subgraph, then you can replace this tree by any other tree and it will still be a tree of the big graph. So you can take any tree here, and also for the tree of the rest, because everything in here gets connected, you can squash this gamma to a single point, and then the remaining edges will be a tree of this contracted graph. So I leave it at that just to illustrate why this formula is true. Okay. So what does this mean? Well, there's similarly, same goes that the f polynomial will be rho to the loops of the subgraph times the u polynomial of the subgraph times the f polynomial of the quotient graph plus higher order stuff. And what this means is that your u plus f scales exactly by rho to the loop number. So what you conclude is that the omega, which I now denote omega of gamma, well, remember we had a term where we sum up all the n's times the lambdas. Right? We had this term lambda dot n, but now lambda is 0 for most of them and only 1 if we have an edge in the subgraph. So this is just the sum over all edges in the subgraph, NE. And then we had minus d over 2 times the power with which the u plus f scales, which we just established is the number of loops in little gamma. And you will realize this is what I've called earlier the superficial degree of convergence of the subgraph. Right? So we get as a necessary condition for the convergence that the superficial degree of convergence, defined in this way, of every subgraph better be positive. Of course, you've all seen this before with arguments in the momentum space representation. The point is, I try to convince you that this is not only necessary but also sufficient. Yeah, so if you do your usual power counting by just looking at all the subgraphs and counting how many edges and loops they have with a dimension, you can formulate it in this way. And the only other thing I want to say in the last minute is that you have to modify this slightly for infrared. So this is UV power counting. Problem. What happens when f of the quotient graph is 0? Yeah. Let's do an example. For example, we have this triangle graph last time where this mass was 0 here, right? M3 was 0. This was a photon propagator. And now let's just look at the scalar integral for this one. Yeah? So no tensor structure. So don't take this picture too literally. I just mean that important thing is that this edge here is massless. And then let's look at this subgraph. Let's suppose this is our subgraph gamma. Yeah? It's a valid set of edges. I can look at the scaling when these two parameters go to 0. Then what is the quotient graph? The big graph divided by the quotient graph means I contract the entire quotient graph to one vertex. So what is left over? Where I have this entire thing, all the vertices are not connected. So maybe I should draw this as an orange vertex. So this is what was previously these two edges. Now you have these two external legs and these legs. All the external legs are now attached to the same vertex. It looks a bit weird. And then the only remaining edge goes to the same vertex, but it's massless. Right? So you're looking at a tadpole graph, which is massless. So there's no momentum flowing through it, right? Because all of these momenta add up to 0. And there's no mass. So there's just nothing kinematical in here. So the f polynomial of this thing is 0. So in this formula, the leading term that I've written down is actually not the leading term, because this is 0. So there's one extra power of rho that you have in the f polynomial. in this case. So what happens in this case is that the f polynomial goes like rho to the loops of the subgraph plus 1, so one more. And then you can still give a formula for the coefficient which factorizes. And now it's a bit funny. So you actually have the f polynomial of the subgraph times the u polynomial of the quotient graph plus higher orders. Okay. And if you think about it, what this means is it's related to infrared divergences, which is exactly what happens here, right? So first of all, you can convince yourself that this is true, right? Because remember, we computed this. So for on-shell external x, we had computed, or you did it as an exercise, that f of this triangle thing was just x1 plus x2 squared m squared minus x1, x2, q squared, right? And now we're saying we're sending x1 and x2, right? These were the edges 1 and 2. We scale them with rho. So the whole thing is quadratic in x1, x2. So the whole thing gets multiplied with rho squared. So indeed, even though we have I have a problem. Do I have a problem? Yeah, let's think about why this is quadratic. My problem is that I wrote loop number of the subgraph plus 1, but here I get 2. And my subgraph is only one loop. No loop, right? So you see, normally what you have in the f polynomials, right? You have a term like the u polynomial times the masses. So you also, if m3 wouldn't be 0, right? You would have an m3 squared x3, right? And oh yeah, I think I just made the formula wrong. Yeah, I think it just has to be plus 1 everywhere. Sorry. But already in this case, right, even if you would have the mass, oh no, sorry, then it doesn't scale. No, it was right. Okay.
Shouldn't we have x3 instead of x1 plus x2?
No, I think that was the polynomial in this case. I'm sorry about that. I'll figure this out until tomorrow. But you know what happens in the momentum space in this case, right? So what happens in momentum space, you have something like, so you have k, you had p and p prime. So this is p prime minus k, and this is p minus k, right? So you have something like k squared, and you have k minus p squared minus m squared, and you have k minus p prime squared minus m squared. And because p squared is m squared, this is the same as k squared minus 2p dot k. And this here is on shell, this becomes k squared minus 2pk. So the problem is, right, for very small k, you have k squared, a k, another k, so you have d4k over k to the 4. So this is a divergence for small k, which is an infrared divergence. which in the scaling should amount to actually not scaling the Schrödinger parameter to 0, but scaling the Schrödinger parameter to infinity. So you would use, you would scale x1 and x2 by, no, in this case you would scale x3 by 1 over rho to make this momentum big. And if you do this computation, you will get this product. Yeah, I think what I should do here is I should scale by 1 over rho, not by rho, in this case. So what I want to illustrate here is that this, even though this might look unfamiliar to you, it's the same thing that you normally do. Right? You do power counting in momentum space in this way, and it corresponds explicitly to something in parametric space. What is the one difference is that in the parametric space, this is a purely combinatorial thing, right? You look at the graph, look at the subgraph, you contract its edges, you count the loops, you count the edges. Whereas in momentum space, you have to be a bit careful, right? If you parameterize the loop momentum a bit differently, it wouldn't look like this. So you have to choose the right routing to see these intra divergences. The other thing is that in the geometric picture with the polynomials, you can easily convince yourself that you have checked everything. Because sometimes you might want to, maybe you've missed some collinear divergence in some region or whatever. So there's also programs for expansion by regions that people use to compute Feynman integrals in certain limits, which compute the Newton polytope and the facets into the corresponding scalings. Okay, I think I want to stop here. So the message of today's lecture was that you can define Feynman integrals as meromorphic functions of the dimension. And the indices, you can work out what the singularities are. You can do the power counting in terms of subgraphs. And this final factorization property, this is really the cool stuff about physics, right? So what this means is that if you go to these boundaries of the polytope, your polynomial actually factorizes into graph polynomials, into semantic polynomials of subgraphs and quotient graphs. So what this means is, for example, in the UV case that I just erased, I think, that what does it mean if you have a sub-UV divergence, which means you get a pole in 1 over epsilon or something, but the residue of this pole will be the product of the Feynman integral of the subgraph times the Feynman integral of the quotient graph. And this is exactly the kind of thing you need for renormalizability to work. You want that the poles, the higher order poles, factorize into counter terms of smaller graphs and quotient graphs. So this recursive structure, that when you go to the boundary of these polytopes, you get actually products of other Newton polytopes of Feynman graphs. This is exactly what makes the story more interesting than just a general polytope or a general hypergeometric function or whatever. Thank you.
We reconvene at 2.